Hello Year 11. Today we're going to look at exothermic and endothermic reactions. On the left here we have exothermic reactions. These are reactions in which energy is transferred to the surroundings. So energy is transferred to the surroundings. Conversely, an endothermic one is one in which energy is transferred from the surroundings. So some examples of exothermic reactions could be combustion, so burning things, oxidation. Some oxidation reactions are exothermic, and some neutralization reactions are exothermic. They can be used for hand warmers. Okay, if it's transferring energy to the surroundings, the temperature of the surroundings is going to increase, so it will warm up. It can also be used for self-heating cans. If we move over to endothermic again, an example of a reaction that's endothermic would be thermal decomposition. And also citric acid and sodium hydrogen carbonate. And a use for this reaction could be in sports injury packs. So if you were to sprain your ankle, you could put one of these packs on, start the chemical reaction, and because it's transferring energy from the surroundings, it will cool down, it will feel cold. And we can represent these reactions using diagrams like the ones shown on the bottom here. So we'll start off with the reactants. I'm just going to use the letter R to represent the fact it's the reactants, and then over here we'll have products, and we should have a line that connects them like this. So the height of this bump as we leave the reactants, this is known as the activation energy. And this is the energy needed to make the reaction take place, so the minimum energy needed for the reaction to take place. Over here with the line that's rising, this represents the energy needed to break the bonds in our chemical compound. On the right hand side here, where it starts to decrease, this represents the energy given out when bonds are being made. We can see here that more energy is given out when the bonds are being made than is taken in when they're being broken, so this is exothermic, so energy is given out. You could also see that the energy of the reactants is greater than the reaction energy of the products, so yeah, energy must be given out to the surroundings. If we look at endothermic, we'll see the opposite is true. So here are our reactants, and then we have a similar bump, and here are our products. Again, this height between the height of the reactants and the top of our curve represents the activation energy. and we can see here that the energy that's needed, the energy that's taken in to break the bonds, is much greater than the energy that's given out when we're making bonds. That means energy must be taken in overall, hence it is endothermic.